Hello, 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 and welcome back to Vocab 4.1. Is that how I do that? Yeah, that's probably right. That's how I do that. V4.1 in Skyward. Alright. What's our words today? Dilation, of course. That's what we're studying. What is dilation exactly? Changes the size and location. I mean, it pushes things around. I mean, all transformations change the location, but I mean, it does change the location. It changes the size and location, but does not change the angles or shape of the preimage. Distances and lengths are multiplied. Oops. And distances and lengths in the preimage are multiplied by the scale factor. Let's draw a picture. I'm going to make my scale factor 1.5. So I went too far. Should be right there. Uh-oh, that's not going to be enough. I'm going to make it 2.5. Estimated 1, 2. Let's just make it 2. No, this is 3 actually. 3. 1, 2. Okay, 2.5 it is. That's right. So that's 2, because there's from the center of dilation, it's 1 distance. Yeah, 1 distance to the thing. 1 amount to the original thing. And if you do another one, that's 2 amounts to the new thing. But I actually wanted to go 2.5. Is this even going to fit? Yeah. Oh, this is short. See, this one's so short. There's 2. There's 2.5. So short things get multiplied up, but are shorter than the long things that get multiplied up. Ta-da! A Butamus post image or image. So we're used to these lines. We had this a lot in translations and even reflections. They are lines that connect corresponding points and the center of dilation in this case. They're not part of the shape, but they are used to enact the dilation itself. They're the action lines. Okay. Speaking of the center of dilation, the point at which all lines that connect corresponding points in the pre-image and image coincide. Coincide rhymes with collide. That's where they all crash. So if I gave you a square and another square, let's see if I can do this freehand. All right, a little bit controversial. I drew a square so that the connecting lines that connect A prime, which is the image, the final, to A, and then it goes this way. B prime connects up to B and then goes this way. And already you can tell where they're all meeting. C prime connects to C and back this way. They're all colliding at D. Yes, D, which is a corner on the original square, is the center of dilation in this case. And everything is connecting back to it. Even like, let's take the midpoint of this side and the midpoint of this side, and voila, they collide at D. You could take the 2/3 mark here and the 2/3 mark here, and voila, they collide at D. A little sloppy in there, but hopefully you get the point. All right. So the center of dilation can be on the shape itself. It could be one of the corners of the shape. It could be some random point inside the shape. Ta-da. The next word is collinear. And what this is about is A prime, A, and D are collinear. They're all on one line. The attribute of being on the same line. This is a funny factoid. Any 2 points in anywhere could be collinear. If all you have is 2 points, you can draw a line between them and they're collinear. But once you have 3 points, it's kind of actually weird to be collinear. It has to be special. In geometry, any 3 points that are collinear have some special relationship. And for dilations, the special relationship is, they're all going to the center of dilation. But even like the edge of a square, well, the edge of a square is a powerful thing. And so all of the points that are collinear on the edge of a square, that's meaningful. Any 3 collinear points, by definition, are like not random. It's impossible, in fact, mathematically impossible to have 3 points all on one line by chance, because there's infinite points. That doesn't mean it couldn't actually happen, but mathematically it's 0. Because what is a point really? How could you even have 1 point? Maybe that possibility is 0. A, B, and C are collinear. This is an important word. Midline. Okay, so the vocab word is actually midline. Midline of a triangle specifically. A triangle's midline. A line segment that connects 2 midpoints of the sides of a triangle. So there's 3 sides. They all have midpoints. If you connect 2 of them, any 2 of them, you'll have a midline. So let's get a triangle. Let's get a midpoint here. I know it's the midpoint because by definition a midpoint splits a segment into two equal parts, and by definition of these little slashy marks, those are, is that 3? There we go. By definition of these little slashy marks, these lengths are equal, and therefore these are midpoints. And now when I connect them, da-da-da-da, midline. Midline. My apologies if I was off screen for that. Okay, one more word and then we'll be done. By the way, there are also midlines here, but usually we'll talk about one at a time. We don't want to get all confusing. Erase that. Don't try that. Last word is ratio. Also sometimes pronounced radio. Just kidding, no one pronounces it that way. A number that compares the relative size of two things as compared. Well, how about the relative size of one thing as compared to another? As compared to another. There's the other. There's the two things. There's the one, and then there's the another. But the number itself actually only compares one of them. If you want the other one to be compared, you just have to flip it over and do the reciprocal. What am I talking about? Here's a line. Here's a line that's twice as tall. If I compare this line to this one, it's 2 to 1. So let's say this is 6 and this is 3, or 6 over 3. But if I wanted to compare this one to this one, it's 3 to 6, or 1/2. So depending on which way you're going, the number is different. But it's just a reciprocal. So you have to know. This may have come up with the IXL. Which one did they want you to compare to? That's kind of that was challenging. I know you guys could handle it, and I felt like you guys needed a good challenge. But the scale factor, it's always quite a bit easier. You just need to know which one's the preimage. But with their ratio of similar shapes, I'd love to hear a report back of how that went. The trick with the scale factor is let's just say this is the drawing for this. Well, let's do it one more time. Let's draw trees, actually. Let's say this is 7 and this is 5. So the ratio of big tree to small is 7 to 5. And in this case, that is the scale factor. If this is the image, so it's not twice as tall. As you can see, it's just a bit taller, just 7/5 bigger, 1.4. No, so not even 1.5, not even 50% bigger, not even 1.5 times bigger, but just 14/10 or 140%. So let's do this. 7/5 equals 140% equals 1.4 equals 14/10. Those are all true factoids that you should love and appreciate. Okay, while we're making a video, let's just figure out what happened here. I think I was thrown off right here. The difference between 7 and 11 is not 2, it is 4. And that makes the comparing these differences 10 to 5, 14 to 7, 22 to 11, 30. So you didn't even need these. I don't even know what's up with those. This is straight up linear. Because a rise of 10, run of 5 10 over 5 is 2, and a rise of 14, the run of 7, it is a rate of 2. So the rate of change here is 2 per 1. It's 10 per 5 and 14 per 7, but if you normalize them all to a 1 unit rate of change, it's all 2 per 1.
Linda Mata, please come to the main office.
Oh boy.
Linda Mata to the main office.
Now, you might be wondering, how could I make that mistake? Well, the explanation is, while I'm making these videos, I'm concentrating so much on explaining that I'm not actually doing the math consciously. I'm subconsciously doing any calculations, and sometimes subconsciously I just not really tracking. All right, so it's kind of funny, hilarious, ha ha ha. All right, have a great weekend.